Here's a big question. It's like the one thing I want you to remember in this course. On the final, this question will count double. Why is it hotter in summer and colder in winter? Okay. I've heard both answers, and so I won't, it's good. There's a correct answer and incorrect answer. Most people get this wrong, and if you're one of them, don't worry about it. You'll get it right now. Most people think it's hotter in summer because the Earth is closer to the sun, and colder in winter because the Earth is farther away. And we'll see some of this a little bit with planets because orbits can be elliptical. Sometimes you can actually be closer to the sun, sometimes farther away. In the case of the Earth, our orbit's almost perfectly circular. This is a to-scale drawing of our orbit. Now, the Earth is not to scale relative to the sun in the distance, but the circle is to scale. It's almost perfectly circular, meaning the Earth's not ever really closer to the sun or really farther away. Technically, it's a little bit closer in our winter, in northern hemisphere winter. Let me ask you about, and we'll explain this shortly, but seasons. When it's summer up here, it's what down in the south? Winter. And so if it was really about proximity to the sun, if we were closer to the sun, it'd be summer everywhere, not just in one hemisphere versus the other. So there's something else at play, and it has to do with the what of the Earth, the tilt of the Earth. That's why all these globes come tipped over. The desktop is the plane of the solar system. And then here we have the Earth, and it's tipped on its axis by 23.5 degrees. It changes a little bit with time. Sometimes it's 23, sometimes it's 24. Changes, wobbles a little bit over the course of thousands of years. But it's locked in pretty much. The way the physics works out, our moon keeps us at that tilt. The tilt was probably introduced when the moon was formed. We'll talk about that later, but basically we think a Mars-sized body hit the early Earth and blew some material off that became the moon and tilted Earth at the same time. That material then locked its axis into place. Interesting little tidbit. But in terms of seasons, the tilt matters a great deal. So I'll turn our sun on here. Sorry if it's bright. Is that too bright for you all? The front row. You're on the back, and no, that's fine. The front row. Yeah. Okay. So we can look at this a couple of different ways. Here, I'll put this figure up here as well. So we have it up here. We also have a scale model of it down here. We have the sun. Yeah, it's really kind of annoying, isn't it? I'll help you out here. And I'll turn the lights out. Oh, I turn them off and say, why are the lights not off? Because I got one right here. Okay. So, here's the idea. Earth is tipped on its axis and it's rotating once a day. But as it's rotating, I'm going the right way, counterclockwise, as viewed from above. It's orbiting around the sun in a perfect circle. I'm not walking a perfect circle because my desk is elongated. But now the Earth is tipped away. The tip stays the same in this direction as we move around the sun, at least over the course of a year or two. It does move very slowly. The tip can change very slowly with time. That's precession. We'll talk about that later. But here we're going around. And when your hemisphere is tipped towards the sun, it's summer in your hemisphere for a couple of different reasons. One is more direct illumination. So you can see it here in the figure. Hopefully you can see it also on the globe. You see the line dividing light and dark. We call that the terminator. So here's the daytime side, and it is, and the nighttime side over here. You can see if you're in the northern hemisphere, the light's hitting you really directly right here at midday in summer. But in winter, you're away. You're kind of drawn away from it. So the light's coming in at a glancing angle and will be spread out over a greater area. I'll demonstrate that with a flashlight on the dark part of the room. I'll go over here. I'll do it right here. So here's direct illumination. The same amount of light. One flashlight, same amount of light. It's hitting this small area. Well, it's hitting all of it, but it's mostly concentrated right here. So you're getting the same amount of light concentrated in a small area because it's direct. So that area is going to heat up. If I have a glancing glow, it's coming in not very direct, and that light is spread out over a much bigger area. Same amount of light, but bigger area. So less energy per square meter. And so this area, this part of the world, will get cooler. So your tilt really does matter, because it can be a significant spreading of the light, depending on where you are on the Earth and where the Earth is in its motion around the Sun.
In this configuration, the light's mostly hitting the northern hemisphere, and it's hitting it directly. It's being spread out over the southern hemisphere, getting less per unit area, so you get more per unit area up here. But in this configuration over here, you're going to get more per unit area in the southern hemisphere and less per unit area in the northern hemisphere. It's always the same amount of light, it's more direct in one hemisphere or the other, depending on how the tilt is oriented with respect to the sun, which just has to do with where we are in our orbit around the sun. So let me check my notes here, see where we are. That's kind of directness of illumination. Oh yeah, let's finish that up there with the concept of horizon angle. So you've probably already gathered, the higher the sun is in the sky, the more direct the illumination will be. Here's a figure that goes along with what we just showed there. And so we can measure that. Now this is not meant to measure angles. I don't know what it's for. It has little suction cups on one end. I guess it's for drawing like circles on a whiteboard. It's like a marker in here. But I'll use it to measure angles. That's all I got. So now your tuition dollars at work here. Let's take North Carolina. Here it is. And I'm going to put it facing the sun. So it's midday in North Carolina. Now the Earth's rotating like this. And when North Carolina crosses the terminator, not the governator, the terminator, this is sunrise. Then midday is when we're underneath the sun. So one of these I'll just put up against the globe on North Carolina at midday, kind of flush with the globe, and that's our horizon. If you're standing on the globe, you're like standing here, and this is the northern horizon, and that's the southern horizon. And with this one, I can orient it towards the sun. I mean, the desk's in the way. I'd do it like down here or something, but just make it go straight out, parallel to the ecliptic, which is the plane, sun-Earth plane. And so this is our horizon, and this is how high the sun is in the sky in summer for North Carolina. It's not directly overhead. This would be directly overhead. So the highest it gets in the sky is an angle kind of like this. I don't know, like 80 degrees or something. But that's summer in the northern hemisphere. We come over here to winter in the northern hemisphere. And this was still pretty direct illumination. It's not straight up, it's pretty direct. But now let's put North Carolina back facing the sun, so it's midday again. Now North Carolina is up here, so the planet's tipped away. And so here's our local horizon there, and move North Carolina towards the sun. And then I'll point this one towards the sun, and that's the horizon angle. At midday, which is the highest the sun gets in the sky, it's only this high off the horizon, off towards the southern horizon. If we're in the northern hemisphere, you'll see the sun towards the south, because we're above the plane of the solar system there. So very low horizon angles. It's just a small angle above the horizon in winter. And you've noticed this. You've noticed that in summer, the sun can get pretty high in the sky. And in winter, even at midday, it doesn't get super high in the sky. If you haven't noticed it, you'll notice it now. This semester, you're going from the end of summer to the beginning of winter, approximately. So you'll see these changes pretty dramatically during the fall semester. Let's take an extreme case. Let's take the case of the Arctic Circle. The planet is tipped 23.5 degrees. So if we go 23.5 degrees down from the North Pole in latitude, we're at the position where the horizon is flush with the sun-Earth plane, the ecliptic. And so I'll just stick it kind of on the Arctic Circle. And here we are in the winter configuration for the northern hemisphere, summer configuration for the south. And so if I point towards the sun on the Arctic Circle, first day of winter, that's the horizon. The sun at midday is just poking up over the horizon. And the rest of the day is below the horizon. So you're going to have just a glimmer of sun and then 24 hours of darkness. And then you get another glimmer of sun. If you go up even higher, if you go up to the North Pole, the horizon's like that, and the sun is actually, it doesn't bend that way, but it's below the horizon. The sun never comes up at the North Pole in winter. Anything above the Arctic Circle, you don't have sun during the first day of winter. And the higher up you go, the longer the span of time is in the orbit when you don't have any sun at all. Come back around here, though. We'll go back to the Arctic Circle. Now our hemisphere is pointed towards the sun. Go to the Arctic Circle and be flush with it there. We have a good angle. So at midday, the sun is up. In fact, if you go to the North Pole in summer, let's see, North Pole is here, it's still above the horizon at midday. And if we actually go on to the other side, the nighttime side of the planet, on the Arctic Circle, that's flush with the ecliptic. And so at midnight, the sun is on the horizon. But the rest of the day it's up. I've always wanted to go up the Arctic Circle in summer. So the sun stays up 24 hours a day. If you're right on the Arctic Circle, it will come down and dip and touch the horizon. But if you go higher up above the Arctic Circle in the first day of summer and around in the summer months, the sun just kind of orbits in a big loop in the sky. It never sets. And if you grew up in Alaska, in a class this size, it wouldn't be unusual if one of them did. This is certainly affecting. You notice that it's always dark in winter, or the sun's up just for a very short period of time, and it's depressing. They actually expose yourself to light so you don't get so depressed up there. Okay, so that's horizon angle, and you can see how it ties into directness of illumination. Okay. Duration of illumination. That's going to be next. Let's take a look at this figure here. And actually, that's right, I don't like this figure because I want everything pointed the same way as my demo here, so I flipped it. I flipped the image, I flipped the words back, but I couldn't flip the graphic of the Earth back, so you just ignore how the continents are weird. But I want everything oriented with the room and with the demo so it doesn't become confusing. So on the left-hand side, we have this configuration here, summer solstice in the north. It's really winter in the south there, though it doesn't say it. And this is winter solstice, again, in the north. And so we have different things marked. We have the Arctic Circle, the Antarctic Circle. It's the same story, just flipped in season. And we have the equator. We have the two tropics, Tropic of Cancer and Tropic of Capricorn. This is 23.5 degrees above or below the equator. And all that these are the points where you can have the sun directly overhead. Like in summer, if you go to the Tropic of Cancer, 23.5 degrees above, you have direct illumination. So if you want the sun directly overhead in summer, you got to go to the Tropic of Cancer and you get it at midday. Tropic of Capricorn is the same deal. You want direct illumination, directly overhead midday in winter. You go to the Tropic of Capricorn, 23.5 degrees below the equator. So we talked about directness of illumination. Let's talk about length of day. You can see it really well in the figure. You can also kind of see it on the globe using the terminator there. Let's consider the northern hemisphere. Here's the equator. If we look just above it, you see that when the tip is towards the sun, most of the northern hemisphere is illuminated. And more than half, definitely. Only this little bit is in darkness. So if you're on the equator, you do have 12 hours a day, 12 hours a night. But you go to any latitude above that, and you have longer days and short nights until you eventually get up to the pole, and it's the extreme case of total illumination all day long. So this goes into our second effect, duration of illumination. The longer you're illuminated, the more you warm up. If we look down in the southern hemisphere, it's the opposite scenario. Most of it is in darkness. Only this little wedge here is in daylight. So again, the equator is 50-50, but as you go farther south, we have short days, long nights, and so it gets cool until you get down below the Antarctic Circle and the sun never comes up. But we switch over to the winter configuration for our hemisphere, and we see the same thing. The Arctic Circle never gets illuminated. Duration of day is 0 hours. And as we move towards the equator, we get longer durations, and then down below in the southern hemisphere, longer than 12-hour durations. So that's length of day, duration of illumination, and both of those effects are tied to the tilt of the Earth. Does all that make sense? Okay. Let's see what else we got here. We got let's just take a little break for some terminology. So these special days, the first day of summer, first day of winter, spring and fall, they have certain names. We call it the summer solstice. Solstice is a technical term. It has kind of ancient meaning to it. And we'll define that when we do archaeoastronomy in about a week or so. Summer solstice, winter solstice and vernal and autumnal equinoxes. So let's define these. This is the first day of summer. And it will also, so that's in this configuration over here. First day of summer. Well, these terms are actually, they apply for either hemisphere. This is summer solstice in the northern hemisphere, winter solstice in the southern hemisphere. Over here is winter solstice in the northern hemisphere, but it's summer solstice in the southern hemisphere. June 21st is not universally the first day of summer. It's only that in the northern hemisphere. In the southern hemisphere, December 21st is the summer solstice. So these are hemisphere-independent terms. First day of summer, and it's the longest day of the year. Again, no matter what hemisphere you're in when it's occurring. Longest day of the year for you at that location. And the sun is highest in the sky at midday. Every day there's a point when it's low in the sky, when it's sunrise or sunset, but at midday it's highest in the sky. This is the directness of illumination, this is the duration of illumination. Winter solstice is the first day of winter. It's the shortest day of the year, and the sun is lowest in the sky at midday. Now the vernal and autumnal equinoxes, equinox means halfway, equidistant. So it's kind of halfway between summer and winter, and it corresponds to when the Earth is either here, whether it's spring or fall, depends on your hemisphere, it depends if you're heading towards summer or heading towards winter, or on the other side. I'm going to take this down for a second. And the nifty thing about the equinoxes is it's 12 hours of daylight and 12 hours of nighttime, no matter where you are on the globe. Here, from your vantage point, I'll get you in just a second, you can see the northern and southern hemispheres. If you're here, 12 hours of nighttime, 12 hours of day. If I come around over here, again, it doesn't matter where you are on the globe. Every point, whether it's up here, down here, you got 12 hours of day, followed by 12 hours of night. Because the tilt is not towards the sun or away from the sun, it's perpendicular, so the tilt does not have an effect at those two locations. So the question is, on the equator, even at the solstices, are the days and nights equal? Yes. The equator, it's always 12 hours of daylight and 12 hours of nighttime, no matter where you are in the orbit. Vernal and autumnal equinox. This is so vernal means spring, autumnal means fall, and it's the first day of each, or either, and it's defined by 12 hours day, 12 hours night. In my last minute, and I know I'm pushing my last minute, but I can wrap up this topic now. Here, I'll kill the sun here. So, go to the other side, and you can do two more exercises in the ebook, and take a look at the next two exercises. I want you to take a note how high the sun is set in the sky at midday. So at midday, kind of around lunchtime, go out, don't look at the sun. I gotta say it twice for legal reasons. Don't look at the sun, go blind. Just kind of block it with your hand. It'll be in the southern sky. And this is the horizon, southern sky's over here. If the sun were on the horizon, it's 0 degrees. We'll go out at midday, and in winter, the expectation is it's going to be low in the sky. This is 0, 45, 90, it's like 30, it's like 60. You can approximate it. Maybe the sun's 30 degrees up, or maybe it's high in the sky, it's like 80 degrees up. That will change seasonally. So you don't have to be exactly at midday, but approximately midday, if you're out changing classes, just take a minute, measure it, write it down somewhere, because I will ask you on exams how this is coming along. And you just have to get it approximately right. I'm not going to ask you, is it 67 or 68 degrees up now? I'll ask you something, is it 30 degrees or 60 degrees up now? Something like that. Also, length of day. Our expectation is we go to winter, the length of day should be getting shorter. And you can keep track of that on the web or just by noticing when the sun goes down. Sunsets will be occurring earlier. Of course, there's confusion once we shift back out of daylight savings time, but, you know, you'll certainly get the feeling there. I just want you to kind of pay attention to these things. You kind of maybe noticed them in the background. Now that you have an academic understanding for it, I want you to develop an intuition going out and seeing it. But anyway, we took a look at, all this was from the God's eye perspective, outside the earth looking down. It's easy to figure out how it all works in that case, but it's a little bit harder to think about it from the ground-based perspective. And I don't think we got to this, so let me explain that. Here's someone standing on just a small little patch of the globe, somewhere in the northern hemisphere. What does the motion of the sun appear like? Well, we just kind of described it, but you can see it here in this figure. During the equinoxes, the sun is rising due east, comes up high, relatively high in the southern sky. Again, we're in the northern hemisphere, so we are above the plane of the solar system, the sun-earth plane. So if you want to look at the sun, you got to look towards the south. So you see the sun in the southern sky, and it comes back down and sets in the west. In summer, our hemisphere is tipped towards the sun, because we've rotated around the orbit. We've gone around the orbit such that our hemisphere is pointed towards the sun, and so the sun is higher in the sky. It will rise north of east, get very high in the sky, but maybe not all the way to zenith, and set north of west. In the winter, when our hemisphere is tipped away from the sun, it's going to be rising south of east, not get very high in the sky, and set south of west. Let me just illustrate that with a laser pointer here. So we've already oriented the room. It's green, so I got to be careful. I didn't pull this out last time, did I? Again, the two sections I forget. So north is that way, south is that way, east and west. So during the equinoxes, I'll be sure not to hit anyone in the eye, because green lasers can blind you. So the sun comes up in the east. It's going to go relatively high in the sky. There I am at midday. And it's going to set over here due west. In the summer months, our hemisphere is tipped towards the sun, so we're going to be rising north of east over here somewhere. And again, this big, giant circle takes a great amount of time. The sun's almost directly overhead, and you're going to set north of west. You can see that there's this big circle. The sun's up a long time and down just a little bit. In winter, we'll be rising south of east, and you have this little path across the sky, not getting too high, and setting south of west. Most of the time is spent underneath our horizon, making it nighttime for us. So all that season stuff makes sense?